Okay, now today we will continue with the Laplace transform. Now we have been talking about the Laplace transform in, if you may remember, it was, so I was saying that the inverse Laplace transform formula could be given like this, which is an awkward integral because it is a line integral along a straight line, along a vertical line at the point of sigma, and vertically extending from minus j infinity to plus j infinity alongside the imaginary position, imaginary axis direction. If you choose sigma to be equal to 0, it would be exactly the imaginary axis. If you choose another sigma, it may be another axis that you are evaluating this. If you choose sigma is equal to 0, then essentially it would correspond to the inverse Fourier transform. But there are some cases where the sigma is equal to 0 or the j omega axis is not included in the region of convergence. Therefore, you cannot really do this kind of an integration. For those, you have to choose another sigma point within the region of convergence. But what kind of an integral does it correspond to, or what kind of an integration output it may correspond to? For those things, I have copied two illustrations from the internet, as you can see here, which illustrates the position of the surface of the S-plane, the surface of the Laplace transform magnitude. This is, of course, in magnitude, the magnitude of x of S or the S-plane. We were talking about poles and zeros. The zeros are like places where the surface touches to the zero position, touches to the horizontal plane, where the magnitude of x of s or h of s, as you can see here, is exactly equal to 0. But the poles, they are problematic because they are diverging towards infinity, as you see. At those pole points, the surface is extending to infinity in magnitude. And the inverse transform that we are taking is like trying to integrate along the imaginary axis, which is here, or along another another line parallel to the imaginary axis with corresponding to different sigma, like this, or like this. Of course, the surface is extending towards infinity, but it's only drawn partially here. If you choose, for instance, the real part of S to be equal to 0, as you see, the real part of S is here, and if you choose 0 to be the sigma value, then it means you are integrating along here, which is like trying to integrate this kind of a curve which may converge, okay, hopefully. Or a similar situation is on the right-hand side image, copy image, where this slice corresponds to sigma is equal to 0. As you see, somewhere for sigma a little bit less than 0, there seems to be a pole. So to the left of the pole, it's the forbidden zone. You shouldn't be taking the integral. Now today I will continue with some further analysis of this magnitude response and a slice of the magnitude response. The magnitude response is this surface, but if you can slice or cut this surface at sigma is equal to 0, it will give you this red curve, or it will give you this profile that you can see here. Okay, how do we discover that profile from the poles and the zeros? Is the next thing that I want to talk about, because it's an important thing, particularly and especially for filters. Because this may be, as these figures are already indicating, these may be h of s. So from those, if you substitute s is equal to j omega, I'm just assuming that the Fourier transform exists. I will substitute s with j omega and I will have h of j omega. And from that, I will take the magnitude of it and take a look at h of j omega. Because we know that this is an important thing for filters, because it gives you the frequency passing characteristics. Is it a low pass filter, a high pass, band pass, etc.? So this is the magnitude frequency response. You may substitute the term frequency with spectral response. So magnitude spectral response or magnitude frequency response, that is the magnitude of h of j omega, which we will try to obtain from h of s. We haven't listed out the properties of the Laplace transform yet, which will greatly help us in solving questions. We will do that within minutes. But we can say that this arrow is available to us if h of j omega exists, which means if the region of convergence includes the j omega axis. So region of convergence must include the j omega axis. And in that case, it also gives us an expression or an idea about a nice system property, which we have been dealing with within the first weeks. What was it? It was stability. So if the region of convergence includes the j omega axis, it means h of j omega exists, and it means the system, of course, this is only for linear and time invariant systems, but this LTI system is stable, it means. The system is stable. So if the system is stable, how can we take a look at what is magnitude of h of j omega? As a matter of fact, the results that I will give you are even more general than that. Even if the system is not stable, unfortunately, still we will be able to find magnitude of h of j omega even for unstable systems, or we may estimate. And the thing that we will do is the following. Let us think of do I have, yeah, an illustration for that? Yeah, it's here. Let us say that h of s is equal to a numerator of s divided by a denominator of s. And the numerator and denominator are, let's say, just put into first order parentheses, like s minus z1 times s minus z2 times s minus z3 times etc. in the numerator, and down in the denominator we have these are z1, z2, z3 are the zeros, of course, because when s is equal to z1 or z2 or z3, the numerator becomes 0, and the denominator will be partitioned the same way, and it will be p1 s minus p2 s minus p3 times etc., where when s is equal to p1 or p2 or etc., then h of s will diverge to infinity. So now let's try to locate these z1, z2, z3, and p1, p2, p3 on the s-plane. This is the real axis. This is the imaginary axis. These poles and zeros are just complex numbers, so they appear as points on the plane. They may be anywhere. Let me put the poles on the right-hand side, like this one, and this one, and maybe this one. So sorry, these are the zeros. So these zeros, they may be on the right-hand side of the plane. They may be on the left-hand side of the plane. I'm not interested in those situations for the time being, but you may understand why I'm trying to put the poles on the left-hand plane. These three, for example. I'm drawing them on the left-hand plane because I'm assuming that the system is a causal system, because it should better be a physical system. Since it is a physical and a causal system, the region of convergence is to the right of the rightmost pole. Because for all of these three poles, the region of convergence is to the right, and the intersection will be the overall region of convergence, which is to the right of the rightmost pole. And obviously, it's this one. Okay. And I want it to include the j omega axis to make it stable, to make it this thing a stable system. So in control systems in the next semester, for example, you will mostly see systems with poles being on the left-hand plane, and you want them to be on the left-hand plane because intrinsically you will assume that the system is causal. So the region of convergence is right-hand sided. It is so much an assumption that even the definition of the Laplace transform has evolved to the definition where the integral of the Laplace transform starts from 0, goes to infinity. It's not from minus infinity to infinity anymore for physical systems because of this right-hand sided assumption, and the stability is therefore requiring us that the poles are on the left-hand plane. For instance, again, in next semester control systems, you will see stabilization of systems where you will put feedbacks to the systems and such tricks, which will try to put or push these poles to the left-hand plane. If there is a pole at the right-hand plane, then it spoils the convergence. So we are trying to push all of such poles to the left-hand plane to make it a stable system. Anyway, that's about stability. By the way, by looking at these poles and zeros, I can see that they are not in reciprocal conjugate pairs. So that's a bad thing because it means that this H of S is a complex valued filter. That's not very physical. If you want to have a physical filter, you should better put a 0 here, for example, then its conjugate, which is here, must also have a 0. And if you have a 0 here, you must have a 0 here. A 0 here, a 0 at its conjugate. And same for the poles. A pole here, a pole at its conjugate. A pole here, a pole at its conjugate, a pole here, and another pole at its conjugate, like this. But I didn't draw it that way because I'm just trying to generalize. So this is a complex filter. That's a pity. But then what is, or how can I find the magnitude of H of j omega? Or how can I estimate it? For this estimation, I will look at the j omega axis. The imaginary axis is the j omega axis, as we know. And along this axis, I will choose a frequency. In fact, that frequency can be changing. So it's like if I move along this axis, it means I'm changing the frequency. Frequency omega is minus something else. It becomes 0. Then 1, 2, 3, 4, increasing in frequency towards the upward direction. So that is the frequency axis that we have here. So on that frequency axis, let's say that this point is the frequency that we arbitrarily choose, then we will alter it, of course. This is omega. For this omega, what's the distance, excuse me, what's the distance between the poles and the zeros and this point of omega? For example, this distance is the distance from that particular pole. This is the distance from this particular pole, and this distance is the distance towards that particular pole. And those distances in the denominator, let me indicate by D. For example, this is D1, this is D2, this is D3. Let's assume that these three are the only poles that we have. So we have D1, D2, and D3 distances. And similarly, we have distances to the zeros. And this distance is to the first zero, for example. Let's call it N1. This distance is N2, and this distance is N3, okay? So h of j omega is a constant times, that constant depends on the overall expression, of course. It can be determined, but it doesn't change the characteristics of the magnitude of j omega. It's just scaling it. If it is a low-pass filter, it will still be a low-pass filter multiplied by C. So, excuse me, I will continue as the following. C times a fraction, a ratio of N1 times N2 times N3 divided by D1 times D2 times D3. If these three poles and three zeros are the only poles and zeros. If you have more poles and more zeros, obviously it will be, in the numerator it will be times N4 times N5, etc. In the denominator it will be times D4 times D5, etc. So the distances to the zeros will be in the numerator. The distances to the poles will be in the denominator. Okay, this is the methodology to construct the magnitude spectral response. All right, it may be a good idea to see it through an example. And the example is as follows. Suppose that we have you are given h of t, it's not f, I'm sorry, it's just an ink spill, it's h of t, is equal to 1 over tau. Tau is the decaying constant of the RC circuit. So I'm trying to give you the impulse response of an RC circuit. E to the minus t over tau u of t. This is the impulse response, it's given to you, but it's a deliberate impulse response because from this you will be asked at part A of this question, you will find what is h of s, and h of s you will find to be 1 over s tau plus 1, where the pole is at the real part of s is equal to minus 1 over tau. Because when s is equal to minus 1 over tau, the denominator becomes 0, and h of s will diverge to infinity. So the pole is at minus 1 over tau. We will have to assume that tau is a positive number r times c, essentially. So minus 1 over tau is somewhere on the left-hand plane, which is good. It's a stable system. And since h of t is something times u of t, and the region of convergence is like the real part of S is actually to the right of or greater than -1 over tau. It includes the j omega axis, and it's a stable system. It becomes a stable system. It's a causal system, right-hand side, as you see. So let's assume that this -1 over tau is somewhere here. And along this j omega axis, let us choose an omega. And with respect to this omega, we will find the magnitude of h of j omega. This is the distance. Let's call it d1. There is nothing else. We don't have a zero or anything. The zero, there's no zero on the finite S-plane. We have only one pole, and this is the situation. So h of j omega in magnitude will be equal to a constant times this distance. By the way, this point is omega point, and the distance d1, the length of d1 we are looking for. What is the length of d1? It will be 1 over, because we don't have a pole, so we put nothing on the numerator. We don't put an n1, it's just 1 that we leave it. And the distance is the square root of omega square plus 1 over tau square, isn't it? Because it's a triangle. This length of the 90 degrees triangle is omega. This length is 1 over tau. Therefore, this is the hypotenuse of this triangle, which is omega square plus 1 over tau square in square root. That will give me this length. What is C? I will come to that. It's even manageable for us to discover the value of C for this particular example. But it will be easier to proceed with the result if you can proceed with the square of this one. Because if you take the square root of h of j omega magnitude square, that will give you the h of j omega magnitude. I want to get rid of this square root in the denominator. So it's actually c square times 1 over omega square plus 1 over tau square. Now I'm telling you that this is the spectral response or the frequency response, and it must be given a name as a low pass or a high pass or a generic some other type of a structure, regardless of what C is. C is just scaling that response. It's just an amplification factor or an attenuation factor if it is small. But is it a low pass filter or a high pass filter? That is something else. I can see that it is essentially a low pass filter because omega, the magnitude of omega or omega square, is in the denominator. And this whole expression becomes maximum, the largest, when omega is equal to 0. It will be c squared over 1 over tau squared. That is the highest magnitude. And as omega increases, as this thing increases, positively or negatively, this h of j omega magnitude will decline. And as omega goes to infinity, the value of this will shrink down to 0. So more or less, the situation is like this. Magnitude of h of j omega starts from a maximal point, and then it decreases to 0. Something like this on the omega axis. So I can say that this is some sort of a low-pass filter. There's no better name to give. So it's a low-pass filter. But what is the peak value of this low-pass filter? The peak value is when omega is equal to 0. And let's come back to this expression, 1 over s tau plus 1. And let us, from here, let's make this substitution. H of j omega is equal to 1 over j omega plus tau. In fact, h of j omega was this. And this is its magnitude. And at omega is equal to 0, when omega is equal to 0, h of j omega becomes 1 over tau. So I expect this value to be equal to 1 over tau. But before that, let me erase it and let me find, in general, the formula for what is h of j omega from this expression. H of j omega in magnitude. So the magnitude of h of j omega, let me find it in square terms, is equal to h of j omega times h conjugate of j omega, which is 1 over j omega plus tau times 1 over minus j omega plus tau. And it's going to be, I multiply the first, or if I make this multiplication, it's going to give me 1 over omega square plus tau square. 1 over tau, these are, this is tau to the minus 1, excuse me, tau to the minus 2. So let me correct myself like this. And that would mean that when omega is equal to 2, 1 over tau square in the denominator will make a tau square. So this was also tau to the minus 1. Where was I making the mistake? That was what I was looking for. I have mistaken the whole concept of 1 over s tau plus 1 with 1 over s plus tau. It was a mistake. So this link and this answer was incorrect. I have to make corrections starting from there, which means I have to make corrections in everywhere. Because I was uncomfortable with the correction or with the equivalent thing, which is incorrect. So I will continue. H of j omega is equal to 1 over j omega tau, excuse me about this, I forgot this, plus 1. So this is more like it. And when omega is equal to 0, so h of j omega is equal to 1 over 0 plus 1, which is equal to 1. So this point is 1. I'm correcting myself. More like this one, yes. And magnitude of h of j omega square is h of j omega times h conjugate of j omega, of course, which is equal to 1 over j omega tau plus 1 times 1 over minus j omega tau plus 1, which will give me 1 over omega square tau square plus 1 square, that is 1. So this is the magnitude square in its correct form. Now you may want to equate this thing to this one. And are these two the same? They must be the same. And in fact, they are the same. It's like this. This thing is equal to, let's divide the denominator and the numerator by tau square. So in the numerator, I put a 1 over tau square. And in the denominator, it becomes omega square plus 1 over tau square. Okay, so I have divided the numerator and the denominator by tau square. Now, when I write it like this, you start seeing that this and this are the same. So this and this are the same. And it also indicates me that C is equal to 1 over tau. Because C square, sorry, it's square, 1 over tau. C is equal to 1 over tau, so C square is equal to 1 over tau square, and that is what we see here, 1 over tau square. So as you see, even if you solve it from the actual h of j omega and try to find its magnitude, you come up with this expression, which is compatible with what we find without finding h of j omega, but instead we found this formula by looking at the distance from the pole, from poles and zeros. Of course, you have to act like this. It's like you are grabbing this red dot here and you're moving it along the j omega axis. And as you move that point, you can notice that this distance will become different. For example, if you choose omega is somewhere here, then the distance will be very large. Then the distance will reduce, and the distance is minimum when omega is equal to 0. The distance will be this much, which is 1 over tau. So actually, this peak value is 1 over tau. It's not 1. When you come here, when you move further to the upper omega values, then the distance will start increasing, and it will go to infinity, of course, that distance. So the denominator will increase for larger omega, and when the denominator increases, the overall h of omega decreases. That's why as omega increases, the magnitude of h of j omega decreases, as you see, to the negative side and to the positive side. This is the general way of looking at the magnitude response. Now, a question that is an interesting question, by the way, appears like this. Suppose that somehow you come up with an example like this. H of s is equal to s minus a over s plus a. So let's assume a is a positive number. What are the poles and the zeros of this? The pole is at s plus a is equal to 0, which is s is equal to minus a. Let's say that it's here, minus a. And the 0 is at s minus a is 0, which means s is equal to a is the 0. So we have one pole and one 0, and they are like this. Now let's choose an arbitrary omega here. And we have to look at the distances from the pole and from the 0. So this is also a. This distance will be d1, and this distance will be n1. Okay, d1 is equal to the square root of omega square plus a square, and n1 is also equal to the square root of omega square plus a square. Let me write it. d1 square is equal to omega square plus a square, and n1 square is also omega square plus a square. So the magnitude of h of j omega is equal to d1 over, no, sorry, n1 over d1. I'm writing it wrong. n1 over d1, which is equal to 1, or c times 1, which is c. So what is the name of this filter? Magnitude spectral response is equal to a constant, or 1, actually. Can you give a name? I'm asking you guys to propose a name for this. You may open your mics and tell me the result, or you may write if you wish. Sampler, Doğukan says. But it's not a sampler because we are not making a continuous to discrete conversion or anything. We're not sampling. This is a filter. So your answer should be like something filter. What filter is this? What pass filter, actually, to be precise? What stop or what pass filter? Band pass. Well, for band pass filtering, it must pass some certain bands, some certain frequencies, and must be emphasized, and some other frequencies must be suppressed, low pass or high pass or intermediate, whatever. But this one is passing just everything because its response is 1 for all frequencies. The name is actually easier than those. It's called all pass filter. It passes everything. That's why the name is all pass. But it's not an identity system. Until now, we have seen only one all pass filter, which was an identity system, where h of t was equal to the impulse response was equal to the impulse itself. So the impulse comes in, impulse goes out. H of t is equal to delta t. And the Fourier transform of delta t was 1. So it also passes everything. An impulse, which is the impulse response, is an identity filter where y of t is equal to x of t. And it passes everything. It's an all-pass filter. But this one is not an identity filter. If you take the inverse Fourier transform or the inverse Laplace transform of this, you will see that it's definitely not equal to delta t. But it is still an all-pass filter. It's just distorting the phase. For instance, if the input is consisting of two sinusoids, one of them is at frequency omega 1, the other one is at frequency omega 2, the output will still be two sinusoids, one with frequency omega 1, one with frequency omega 2, and their magnitudes, the magnitudes of these sinusoids will not change at the output, but their phases, their angles, their positions with respect to one another will change. It's just changing the phase. This is a phase changing all-pass filter, but the magnitude-wise situation is it is passing just everything. H of j omega magnitude over the omega axis is 1. It's just passing everything. It's an all-pass filter, but it's not an identity filter. To see that it's not an identity filter, we must look at its phase response or angle response too. We have been looking at the magnitude of h of j omega, but there is also the angle of h of j omega sorry, the last part is unnecessary. There is also the angle of h of j omega that we must take a look at. And for that, we haven't seen the formula yet. Let me quickly show you that formula, but I have to indicate that it's not necessary for you in the final examination. I don't intend to ask questions regarding plot the angle response kind of questions. I don't ask them, but I do ask magnitude response related questions. But we have to know the angle response too. Let's check. I'm going up a little bit and I'm coming back to this place. The magnitude response, I said, is respective to the distances from the poles and the zeros, and the angle here is the angle related with n1 plus the angle related with n2 plus the angle related with n3 minus the angle related with d1 minus the angle related with d2 minus the angle related with d3. And what are these angles? The angles are as follows. You you zoom to here. Let us zoom a little bit. You draw a horizontal line, and this angle, for example, is the angle of n1. Okay. That is what n1 is, and that's how you find it. The way to find it, of course, it's an arctangent operation. And it's not very easy. It's a little bit more complicated than what we usually do. If you have multiples of poles and zeros, it may be getting complicated. But if you have a single angle, like the example that we have here, what was the example? Yeah, here it is. So this is the angle that I'm looking for. So the angle that we are dealing with is this horizontal line, and the angle is here that we have. And that angle is the negative tangent of this angle. You see, that angle is almost the same. It's 180 degrees more than this angle that we have. And that angle that we have for this question, let me try to solve it at this part. It's the angle of h of j omega is equal to the angle, that small angle, which is arctangent or tangent inverse of the height of the triangle is omega, and the width is 1 over tau. 1 over tau. But since the angle is more than 180 degrees, it becomes negative. And you can also think that it's negative because it's in the denominator. So the denominator angles you take as negatives. And that is minus tangent inverse of omega times tau. Can you try to plot this? Yeah, you may plot it if you wish, but that wouldn't be necessary. However, talking about the same example, let's roll back to that example. I said that the shape is in a low pass filter and it's decaying like this, but it's always a good idea to put some legends at some particular points. So let us start from here. We know that when omega is equal to, it's not 1 over tau, it's 1. I'm correcting it for the third time. When omega is equal to 0, It is 1 over tau square over 1 over tau square, which is 1. And when omega is something, we come to a certain point, and that omega is equal to something is when omega is equal to 1 over tau. When omega is equal to 1 over tau, the numerator will be 1 over tau square, and the denominator will be 2 over tau square, because 2 of that 1 over tau squares will be contributed from this and from this. So when omega is equal to 1 over tau, we come to a point which is 1 over square root of 2. Same here for minus 1 over tau. So we come from 1, it reduces to a point or a value which is 1 over square root of 2 times 1. That 1 over square root of 2 decrease point was a critical point from circuits, you may remember. Do you remember that? From circuits, you must have seen this place where the response is reduced by square root of 2. That is a point with a name. Cutoff frequency, yes, cutoff frequency. This is known as the cutoff frequency. So the cutoff frequency of this low-pass filter, it's a bad one, but it still has some cutoff. That cutoff frequency is 1 over tau. Omega is equal to 1 over tau. That is the cutoff frequency. Or you may also remember the minus 3 dB, because if you measure everything in decibels, this is the minus 3 decibels point, where the magnitude reduces by 3 decibels. And beyond it, it means it is reduced too much. So this is the actual shape that we have drawn, which is a better shape than the, what was the name of the shapes that, the plot that we were plotting? Do you remember? I do remember the plot. No. This looks like a Gaussian, but that's not what I'm asking. The plot of the frequency response of a circuit. For the cutoff frequency, from the cutoff frequency, you draw a straight line and it goes down, okay? In circuits, you may remember. If you don't, let me tell you, it was called the Bode plot. No, it's the Bode plot. The Bode plot is like flat, and then it reduces, and that is the cutoff frequency. But the Bode plot is just straight line approximation in decibel scale, as opposed to this h of j omega plot. This one is the real and the actual frequency response, magnitude frequency response. So it's better than the Bode plot. It's more accurate, but Bode plot is just an approximation. You say that there is a cutoff or minus 3 decibels point, you draw it straight up until there, and then you draw a straight line going downwards. That was the Bode plot that you learned. So in signals and systems, now you have learned an improvement of the Bode plot. This thing, you can also call it a Bode plot, but not an approximation without the straight lines, and it's not on the decibels axis. It is the real, actual magnitude of h of j omega that we are drawing. And we are drawing it by using this philosophy, the distance from the poles and the distance from the zeros. It helps us to develop many other fascinating filters. For example, this is an all-pass filter that we can make. So if you want to equalize a filter, for instance, that is the trick. In the old days, in the old hi-fi systems, so-called hi-fi, they were not very high fidelity anyway. There used to be equalizers in the musical systems where people are trying to equalize lower frequencies by improving or boosting the lower frequencies and the higher frequencies by meanwhile suppressing the mid-range frequencies, because it is heard better that way, a better fidelity. But the actual system-wise characteristics way of equalization is the following. Let's see it as an example. Suppose that your h of s is equal to s plus a over s plus b. Okay, suppose this was your system. How do you equalize this system? The way to equalize it is, if there is a zero at a, let's put a pole at minus a. Sorry, the zero is at minus a, so let's put a pole at a, s minus a. And we put, since there is a pole at minus b, let's put a zero at b, which is s minus b. We artificially incorporate this as an equalizer. Because now we know that the magnitude response will look like this. Every time we have a pole, now we have a zero at the right-hand side with the same distance. And if we have a zero here already, let me draw it in a different color, a zero here, then we have incorporated a pole here. So when you take a look at the distance to the poles and the zeros to any omega point, you will see that the distances to the zeros and the distances to the poles will be exactly the same. So h of j omega will be equal to a constant times 1, which is a constant. So we make it a uniform response filter. We equalized our system to make it an all-pass filter. Some questions I want to ask within a few minutes. I'm not going to solve them, but I want to emphasize something. Suppose that in a system we have, sorry, that was a bad place. We have these three, still I'm not happy with this. Let me put these two poles. This is the j omega axis, this is the sigma axis, and we have a zero here. The question here is, can you plot the magnitude response? H of j omega over the omega axis. Can you roughly plot? Or if I give you some plots of magnitude of h of j omega and some other plots on the S-plane. This is the S-plane. Can you match which one could be which? Now, here you see frequency, let's call it omega 1, and here it is minus omega 1, of course. When your frequency comes from 0, when the frequency is 0, by the way, h of j omega is equal to 0 because there is a 0 of the system at omega is equal to 0. So let's move up a little bit. As you come closer to this pole, the distance between the pole and the frequency becomes smaller and smaller and smaller and smaller, and it's in the denominator. Of course, there will be other distances from this 0 and from this pole as well. But the decisive thing will be the distance to this pole, because it will be too small in the denominator, and if you multiply with that small number, the denominator will be very small. If the denominator is small, the frequency response, magnitude response will be larger. So I would presume that it will reach to a peak at around omega 1. And if you move further towards up, there will be a distance from this in the numerator and two distances from this one and this one in the denominator. And as you go upward towards infinity, there will be two infinities from the poles, two infinity distances from the poles, and one infinity distance from the zero. So one infinity divided by multiplication of two infinities, infinity over infinity times infinity. It will shrink down to zero because the number of poles is less than the number, the number of zeros is less than the number of poles. So the denominator will be growing larger, and that's why it will be decreasing to 0. And at the negative side, the situation will look more or less the same. Around minus omega 1, it will reach to a peak, and after that, it will shrink down to 0. So h of j omega will look like this. Now, can you give a name to this h of j omega, by the way? I'm expecting names from you now. No one is typing anything. Can you give a name to this filter? It's not band stop, but it's band pass. It is essentially passing around this omega 1. No, it's not high pass. It is something like a high pass, but as frequency goes to infinity, the passing reduces back down to 0. So it's not passing much for high frequencies here and here, and it's not passing at low frequencies, but it's passing only the mid ranges. So it's actually a band pass filter shape. The proper name for this one is a band pass filter. So how did I design this bandpass filter? By deliberately putting the poles to somewhere around the passing region, and I'm making them as near as possible towards the j omega axis. I locate them near to the j omega axis at the point where omega is equal to omega 1, around that point. But it's not a good bandpass filter. Can I improve it? Probably I can by putting, for instance, two poles here and the 0 here, another 0 here. So this is also an S-plane, and correspondingly, I strongly believe that according to my experiences, this will look like this. So this one was incorrect. Because of these two poles, now I seem to have two ripples around this, which makes it not as peaky as before, but makes it a little bit more flat. If I put 3 poles up and 3 poles down, it will be even flatter. So I'm trying to make this region a little bit flatter. And if I can make it even more flat, it will be a better bandpass filter, because bandpass filters are supposed to pass everything equally around the passing band. And this point, by the way, is also a little bit more flat as opposed to the previous one. The previous one was like this, but now it is like this, a little bit flat, more flat, because of these two zeros here. I could put more poles and more zeros, like another 0 and 0 here, and another pole here and here. That would still be a good, relatively good bandpass filter. It's going to be even flatter around this range. That is the passing frequencies from here to here, let's say. And it is stopping here. So these are the stop, these are the pass. If I want to pass, I put a pole near to those frequencies. If I want to pass around the frequency range, I'm just putting poles over there. But the total number of poles and zeros is also critical here. If you make the total number of poles and zeros to be exactly the same, equal, then the numerator will be n1 times n2 times n3. For example, you have 3 zeros and 3 poles. Denominator 1 times denominator 2 times denominator 3. If you move your frequency along plus infinity or minus infinity, these all will go to infinity, each one of them, and these all will go to infinity, each one of them, equally. Therefore, at omega is equal to infinity, it will make non-zero, a value, a constant value. So h of j omega as omega goes to infinity will attain a finite value. If you put one more numerator, then the numerator will go to infinity more. So h of j omega as omega goes to infinity will, the magnitude of h of j omega will go to infinity around the tails. So you shouldn't really have more zeros than poles. Otherwise, your system, h of j omega magnitude response will diverge to infinity around the tails, always. However, on the contrary, if your denominator amount is more, that is, if you have more poles, then the denominator will go to infinity, which will make h of j omega to shrink down to 0. Okay, they will go down to 0 as omega goes to infinity, which is a desirable property. All the filters, most of the filters are expected to attain a 0 value, except high-pass filters. High-pass filters will probably have equal number of poles and zeros because they will go up and they will stay there. We want them to stay there towards infinity. This design issue of locating poles and zeros is a very nice and valuable tool that every signal processing student is expected to learn. It's called filter design. So what we are doing here is filter design. We're just locating the poles and the zeros and looking at their frequency responses. We are designing these filters. Once you have the poles and the zeros, you can always take the inverse Laplace transform and see what's happening in the time domain as an impulse response, or every pole and every zero corresponds to one capacitor and one inductor, essentially. So you're just choosing the value of your capacitor and the inductor of your RLC circuit according to the locations of these poles and the zeros. That's a circuit design. But first things first, you have to start from filter design, then you go to circuit design, and then you implement it. That's how we make filters. That's how we design filters. And that's a good thing. Okay, we are already too late for the first hour. Let's give a break. We will start at 10:20. Okay. At this hour, let's meet again and let's continue with our discussion. Now I'm stopping the recording and ending the meeting right now.